Welcome back to problem 3.5. We will start solving the exercise now. So what we will look at first is trying to find the distribution function and an expression for the density function. So we will let t be greater than equal to 0. Then, based on the formula in the book that we have from here, we know that the distribution function is given by the exponential of minus the integral from 0 to t of the mortality rate. And our mortality rate is constantly equal to lambda. So what we have is e to the minus integral from 0 to t of lambda ds. And this is exactly e to the minus lambda t. Because lambda is constant, the integral is just the constant multiplied by the length of the integral. So we've got this part. Then we look at the derivative. So the derivative, or the density. We look at the density, which is the derivative of the distribution function. The exercise tells us very neatly. So the distribution function is actually equal to 1 minus the survival function, which is also the reason why this is equal to the negative value of the derivative of the survival function. And we already have the survival function. It is up here. And that means we can just take the derivative of that and put a minus sign in the front. So what we have is minus lambda multiplied by e to the minus lambda t, and the two minuses cancel, so the density is now confirmed to be lambda multiplied by e to the minus lambda. So that was part 1. Well done. Now we want to do part 2, showing that the conditional survival function does not depend on x. So part 2. What we do is we say, well, let t be greater than 0, right? And let x be given arbitrarily. So we choose any x in the world. Because then, when we calculate the conditional survival function, tpx, we see it is equal to the, well, we use this formula they give us up here. We can also see this formula in the book. So the probability of surviving past age x plus t, given that you have survived past age x, and this, when we plug in our survival function, given by this expression here, this is just equal to e to the minus lambda of multiplied by x plus t divided by e to the minus lambda x. So the x parts cancel out, right? And what we have left is e to the minus lambda t. And lo and behold, that certainly does not depend on x. And in fact, what we see here is that this is indeed equal to the probability of survival for the next t years, given that you are 0 years old, since the survival function in 0 is equal to 1, right? So this is equal to TP0, which was exactly what we needed to show. So in conclusion, since x was chosen arbitrarily, TPx is equal to TP0 for all x greater than 0, hence is independent of x. Now, if exercise 2 went a bit too quick for you, and you're like, hey, what went on there? Then it is probably because you have not yet understood the expression TPX. So just get that notation, become familiar with it. So just to freshen up, TPX is the conditional survival function. And the conditional survival function, TPX, is equal to the probability that a newborn survives past time t plus x, given that the newborn survives past time x. And this also is what we call the probability that the remaining lifetime of an X-year-old is greater than t. TPX. So the way we see that TPX is given exactly by this fraction here is based on how it looks when we write up TPX as the conditional survival probability here, because the t, the lifetime t, is distributed according to this distribution with this survival function. And what we use here is just the formula for conditional for conditional probabilities. So if this part if you feel it's hard to understand this part, then read this part in the book again and again and again, and soon you will get it. Okay, so the last thing they want us to do is to conclude that the survival function in x plus t is equal to the survival function in x multiplied by the survival function in t. So let's just take a look at this. F bar of x plus t. Well, we already had the expressions, right? We concluded much earlier that the survival function at any non-negative value t is given by e to the minus lambda t. So this thing here is equal to e to the minus lambda x plus t, and this is equal to e to the minus lambda x multiplied by e to the minus lambda t. And that is equal to, respectively, the survival function in x and the survival function in t. Very nice. So let's just round off with a simple interpretation of this. This means that the exponential law has no memory. And what do I mean by that? Well, the thing I mean by the exponential law has no memory is that what we see here is the probability of a newborn surviving the next x plus t years. So if I have a timeline, I have x here, and then x plus t here, and 0 here. So the probability that a newborn will survive this entire span is given by the probability that the newborn survives this entire span, plus the probability, multiplied by the probability that the person kind of becomes newborn again here and then survives the next t years. So this means that the exponential law has no memory, in the sense that survival in one time period and survival in another time period are actually, they're kind of independent from each other, because it is when we have independence that we're allowed to multiply probabilities together. So that was problem 3.5. See you in the next exercise.